Thank you, Srija. Good morning, everyone. I am Basanti. Currently, I am a final year MSc student here at the School of Astrophysics. Today, I will be talking on my ongoing MSc project, Study of Galactic Center using Neutrinos and Gamma rays. My supervisor, Dr. Devanjan Bose from Central University of Kashmir, and my co-advisor, Dr. Shomadip Shamu from here at School of Astrophysics, and my collaborator, Dr. Jagdish Joshi from Aryabhatta National Institute of Observational Sciences. Okay, so let's start with the motivation of doing this project. Here is the image of the plane of our galaxy Milky Way, Akash Ganga, in photons with different wavelengths from radio to gamma rays. But now, beside the light, we have the image of our galactic plane with neutrinos. And we see diffuse neutrinos throughout our galactic plane. The largest neutrino telescope, IceCube, they have detected very high energy neutrino emission from our galactic plane. Also, in the last few years, several air shower experiments like the HAWK, the High Altitude Water Cherenkov Observatory, and LASSO, the Large High Altitude Air Shower Observatory, they have detected very high energy and ultra high energy gamma ray emission from our galactic plane, and that is stronger towards the center. And also, they have identified so many ultra high energy gamma ray sources in our galaxy. So all these results are suggesting that these emissions are related to cosmic ray, and there must be some PV cosmic ray accelerators in our galactic plane. And most likely, there is hadronic mechanism, and the neutrino detection immediately guarantees the cosmic ray source. Now let's see what is this cosmic ray and how it is related to the gamma ray and the neutrino. Well, cosmic rays are the high energetic particles, mostly protons, coming from the outer space. It was first discovered by Victor Hayes in 1912, and they are continuously hitting our Earth from all the directions. And when they enter in the Earth's atmosphere, they interact with the air molecules and produces the secondary particles that we call the air shower. So we are now all under this shower. This is the observed cosmic ray spectrum that shows the cosmic ray flux with the corresponding energies. And we see that the flux is decreasing with the increase of energy. Now, we have the world's largest particle accelerator, the Large Hadron Collider at CERN. The highest energy at which the particle gets accelerated from it till today is 1.18 TeV. But now, here you can see the cosmic ray energy at 10 to the 20 eV. So now think a teeny particle like a proton whose rest mass energy is some 938 MeV is accelerating in such huge energy. And then what are the processes in our universe that are accelerating particles to such huge energies? So there must be some sources in our galaxy that can accelerate particles to PV energy that is 10 to the power 15 eV or more than that. That is called the PeVatrons. So the question is, what are the PeVatrons? What are the emissions mechanism and the acceleration mechanism happening there? And thus, the most mysterious problem, the origin of cosmic ray. Now, there could be several acceleration mechanisms, but before that, we have to consider some condition in the acceleration side. Like when a particle is accelerating and there is magnetic field, so it will have the Lama radius. Now the Lama radius should be less than the source size to confine the particle in the source. And thus, for our galaxy, we can see the maximum energy for a particle to be confined within our galaxy is 10 to the power 18 eV. And there will be other conditions like the interaction losses or the radiation losses that should be less than the gained energy. And overall, it should explain the observed cosmic ray spectrum. And considering all of these, the diffusive shock acceleration is the most efficient one. Now the question is, how can you identify the cosmic ray sources? Now, as cosmic rays are charged particles, so they get deflected deflected by the intervening magnetic field. So we can't trace back the cosmic ray origin. We need some neutral messengers, right? Now think, this is the origin of the cosmic ray, and the cosmic ray can interact with the matter field and the ambient photon gas, and thus it can produce the pions. The pions then decay to gamma rays and the neutrino. So if we can detect these gamma rays and neutrinos, then we can indirectly detect the cosmic ray. But gamma ray can be produced in other ways, like the inverse quantum scattering or the Bremsstrahlung mechanism. They can't guarantee the cosmic ray origin. But neutrinos are only produced through the hadronic interaction. So they immediately implies the cosmic ray origin. So neutrino is a very unique messenger to us. Now here is a brief introduction of the neutrino. Neutrinos are the elementary particle of the standard model of particle physics, and they interact by gravity and weak force only. And they are everywhere. Like for an example, at this moment, about 65 billion neutrinos are passing just through your thumbnail per second. But their interaction cross section is very small, like 10 to the power minus 37 per centimeter square. So if 10 to the 37 neutrinos pass through a very dense material, then only one interaction can happen, like such an introvert. But the thing is, as they are neutral, they are undeflected, and they are very weakly interacting. So they are carrying the cosmic stories, the histories of our universe in their heart. Well, now go back to the question that what could be the cosmic sources in our galaxy. For this, here is a rough estimation of the energy that a source should produce to be a cosmic resource. And we can see that if a source can produce an energy of 10 to the power 54 eV per second, then it can be a cosmic resource for our galaxy. Now, there are several sources that have been proposed to be cosmic resources, like the supernova remnants, the pulsar wind nebula, the star-forming region, and the microquasars. So the question is, are they the galactic PeVatrons? Can they accelerate particles to 10 to the power 15 eV or more than that? Well, now from the very recent observations, the Lasso and Hawk detected ultra-high energy gamma rays from the jets of the microquasar. And they are suggesting that these gamma rays are originating from the hadronic mechanism in the microquasars. So here is a brief description of the microquasar. Microquasar is a galactic binary system composed with a compact object and the star. The compact object accretes matter from the competing star and giving rise to the jets. Here is some features of the microquasars. Now, obviously, our question is, can microquasar be the galactic PeVatron? Can they accelerate particles to 10 to the power 15 eV? And can there be the hadronic mechanism so that we can get the gamma rays and neutrinos from the microquasar? So I am working on the microquasars, like how they can produce the gamma rays and neutrinos through the hadronic mechanism. So for this, here is a mechanism for the production of gamma rays and neutrinos from the hadronic interaction in the microquasar. You can see the jet. The compact object is accreting matter from the star and giving rise to the jet. And we have considered a high mass, very windy stellar object so that the wind can penetrate into the jet, and then the jet proton and the ion of the stellar wind can interact, and then by hadronic interaction we can get the gamma rays and the neutrinos. We have here assumed, for simplicity, we have assumed that the jet axis is perpendicular to the orbital radius, and we have considered a jet disk coupling hypothesis. That means the total jet power is scaled with the disk accretion rate. We have also considered the energy distribution of the jet proton to be a power law like this with proton index alpha. Now, first I am considering the gamma ray emission. So from proton-proton interaction, neutral pion decay produces, and from the decay of neutral pion, we can get the gamma ray. And from this, by some step-by-step calculation, we can get the luminosity of the gamma ray from the pion decay. And that depends various parameters of the jet, the stellar companion, and also the overall system. Now, our work is to apply these theoretical models to some microquasars and then compare with the observational results. Okay. So for this, first I have taken the microquasar SS433. From the very recent observation last year in November, Hawk detected ultra high energy gamma ray from these microquasars. This orange data points are the Hawk data, and then I have applied my model, and I have get this blue. This is from the model fitting. So we are getting the fitting well, but I have just started with this work, and I have to study more specifications of the parameters and with the tune, like how we can get the best fit. For here, this is the parameters that I have used to get the fit. So in my future goal, I will apply this model for several other microquasars and try to compare the results. And as I am considering the hadronic mechanism, so there will be the neutrino emissions too. So I will also try to generate the neutrino flux from the microquasars and then try to compare the results with the existing or the upcoming neutrino telescopes. So in this project, our aim is to explain the observations with the theory and then enhance our understanding of the astrophysical phenomena and thus contributing to identify the cosmic sources in our galaxy. So the future seems very exciting, and thank you.
Thank you, Basanti. Thank you, Basanti, for your wonderful talk. Now, questions from the audience. Yes, please.
Here, one of the slides, you have cross sections of the reactions. So, can you explain what is the cross section?
Cross section of which reaction? Proton-proton?
What is meant by cross section? Explaining the idea of cross section.
Like when I am saying that cross section, interaction cross section is 10 to the power minus 37 per centimeter square. So that means for 10 to the power 37 particles going through a material, one interaction happens. Per centimeter square, like per unit area.
Yes.
Yes, for the neutrino cross section.
Or predicting.
I haven't predicting any cross section. This is some standard value. 10 to the power minus 37 per centimeter square for 1 GeV neutrino.
There is some, some standard notation for standard notation for cross section units.
Hello.
Yes, that is the millibarn, like the barn.
1 bar is how much centimeter square?
I can't recall actually. Sorry.
Questions?
On the slide of acceleration mechanism, from where are we getting the conditions that you mentioned?
This.
So yes, so you mentioned certain conditions here on which you are basing your theory and your computation or any of your model. So where are you getting this kind of conditions?
These are all the theoretical concepts, like the interaction, like when a particle the losses its energy by radiation, that should be less than the gain energy, right? Otherwise, we will not get the sufficient energy for the accelerated particle. Other is the particle confinement. Like if a particle is not getting confined in our galaxy, then how can we detect the particle?
Any more?
You can briefly explain the jet coupling hypothesis and the jet coupling constant balance, how it is being formulated?
Did you get the question?
Yes. No, I don't know how the jet coupling constant values have like calculated or something.
So, but what
Typically, its value is like 10 to the power minus 1 to minus 3. So, my fitting, I have taken it like 10 to the power minus 3. Jet coupling hypothesis is tells like the total jet power that is scales with the disk accretion rate. Like the jet is the compact object is accreting matter from the stellar object.
Thanks. Thank you, Basanti.
Thank you, everyone.